Greetings, physicists. This video will be about how to solve problems involving work and power. So we're looking at a sled dog tugging his sled across the snow. Constant speed, we're going to underline that, that's going to be important. And he's using a force of 350. We're curious, how much work does he do? And then later we'll be curious about where the energy goes. So we got the snow, we got the sled, we got the dog, and we can label some things. The distance they're going to travel is 4.9 meters. We know the dog, and the dog is pulling this way on the sled at 350 newtons. And that's it. Well, we also know there's a constant speed, so we know that A is 0 meter per second squared. Well, let's look at the work equation. Work is the force times the distance. Pretty straightforward. That dog has a force of 350 newtons times a distance of 4.9 meters. Okay, let's pop that in the old calculator here. 350 times 4.9. I get 1715 Newton meters, which we will also call a joule. So the dog does that much work, definitely, because he's pulling the same direction the sled is moving. Where does the energy go? Because the sled is at constant speed, it's not increasing its speed. You would expect, if you did work on something, for it to gain some kind of energy, like speed energy, kinetic energy. Well, what's happening here, no, that's just stay put, okay. Constant speed means that the dog's 350 pulling this way is not causing an acceleration. Well, that's only true if there is a backward force on this sled of 350, a negative 350. What's causing that force? Well, most likely candidate is probably friction. So, even though the dog does 1715 joules of work, that friction force acts on the sled over the same exact distance. So all that energy the dog's putting in is getting taken right back out by friction. And when friction does work on something, the kind of energy you gain is heat. So, as the sled is being dragged across the snow is warming up. The energy being drained by the resistance, the friction force between the sled and the snow, is going into the runners. The runners are going to heat up a little bit. The snow is going to heat up a little bit, might melt a little bit. But that's where the energy goes. It's absorbed into the two surfaces that are rubbing together. And you've experienced this with your hands. If you rub your hands together real quick, you get friction and you feel them heat up. Well, that's where the energy is going, because your hand doesn't keep accelerating. All right, on to the next one. Airports, who loves them? You got an old suitcase. Man, I used to have one of these as a kid. It was a big leather job, had little wheels on the bottom, and a strap. I loved it at the time. I don't know what I would think about it nowadays. We make that strap a 45-degree angle right there, and here you are holding it and making your way through the airport like so. Now, where you apparently are going across the airport 120 meters, so you travel like this, and the strap, we wrote the 45-degree angle in. There's a tension in the strap of 20 newtons. We ask, how much work do you do on the strap? Well, let's draw a free body diagram, shall we? I mean, really, we don't need to draw it so much as just draw that tension arrow. That tension arrow here is 20 newtons. Has an angle of 45. And that means there are component forces. And those are going to be sine and cosine. So 20 cosine 45 and 20 sine 45. Those are both in newtons. So you ask yourself, well, which one of those forces is doing work? Although I think the easier question is which one is not doing work. And this force here cannot be doing any work on this guy. Because look, that component force is pulling straight up. But it doesn't go up. The bag does not move upwards. So this force does not cause any displacement. And we only consider work to be a force that causes a displacement. So the thing has to move in order for you to do work on it. You can push on the building all day. You will not have done any work on it if it doesn't go anywhere. So this is actually the only force we can use or the only component force we can use, because it actually caused the thing to go 120 meters. The upward force did not. The upward force just lightened the load, made the normal force less. So let's do our equation. Work equals force times distance. And in our case, the force was 20 cosine 45 newtons times the distance it went, which was 120 meters. 120 meters in the direction of that 20 cosine 45 newton force. So plug this in. 20 by 120 cosine 45. I get another big number. 1697. I'm probably going to wind up rounding that. I think this is a 2 sig fig problem, so we'll round that to 1700 joules. 1700 joules of work. Not a bad workout. Actually, it is a pretty bad workout. That's not a lot of energy. All right. A 100 kilogram weightlifter performs a lift. Speaking of a workout, a 100 kilogram weightlifter is doing the clean and jerk. Never seen a clean and jerk. It looks like this. You got a barbell, and the dude bends over like that, and then just kind of stands up. But he doesn't just stand up. That would be a deadlift. He lifts it all the way over his head in one sort of smooth motion. There you go. There's our clean and jerk. Okay, we have that the bar is a 190 kilogram bar. We have that the dude is a 100 kilogram dude. Raises the bar up from the ground to here, and apparently that is a distance of 1.9 meters. And he does it in a delta time of 1.8 seconds. Now, the thing that confuses me about this question is the dude stood up, but he didn't travel 1.9 meters. His center of mass didn't travel 1.9 meters at any rate. His center of mass is maybe where his stomach is, so it went from there to up here somewhere, which is like that much. I mean, his arms went up, certainly, so maybe it got a little higher because of his body position. I think we have to assume for this one that we're not going to be able to tell how much of his own weight went how far. We don't really know that. So we're going to have to ignore this 100 kilograms. That's a distraction. Don't let that get into your calculation here. Because the only thing we know for certain how far it traveled was the bar, and that bar had a mass of 190. So the work done here looks like a force times a distance. The bar traveled in a straight line. There's no cosine business we have to deal with here. This is all one-dimensional motion. Oh, and, sorry, that's the work equation, but we also want the power equation. The power is just the work divided by time, because they're asking for power. But notice that the force that he used is not given, so we're going to have to substitute. Instead of the force, he's lifting the bar straight up, so this is an mg. It takes an mg to lift that. So let's plug this all in. The power, if we sub all that into power, the power will be the mg, that was the force, times the delta x. That's the work on top, and then delta time on bottom. And then substituting, we should have 190 kilos times 9.8 meter per second squared, and the delta x was 1.9 meters, all divided by 1.8 seconds. Let's see what that comes out to. 190 times 9.8 times 1.9 divided by 1.8. Another big number, all right. Big numbers for energy. 1965 joules. Yeah, this is another 2 sig fig answer, so we'll round to there. So about 2,000 joules. So apparently one clean and jerk is almost the same amount of energy as dragging your suitcase across the airport. So you guys who want to save your workout time, you don't have to go to the gym as often, fly more. Okay. A ranking task. We love these. Right, we got four dudes, each of them climbing a set of stairs, and they have mass and they have a certain time interval, and we want their power outputs from biggest to smallest. I'm going to go ahead and label this A, B, C, and D just so we can tell them apart. Looks like the first three guys have a staircase that's 10 meters tall, and the last dude has one that's 20 meters tall. All right. We have three guys that have the same mass, and we have two guys that have the same time. So there's some comparisons to be made here. We can definitely say, so power output between guys of differing masses. If you have more mass and you lift yourself up the stairs, you're doing more work, right? So power, just like in the last problem, power would be mg delta x over delta t, because this is a vertical lift. They're taking themselves straight up. Not straight up, but it's the vertical component that matters. Gravity only pulls straight down. So only the work they do straight up counters it. So between two guys with different masses, the one with more mass has developed more power because they have the same time, they have the same gravity, and they are both climbing 10 meters. So we'll say that B is more power than C. B greater than C. If we look at B compared to A, B does in less time, and when time's on the bottom, that's an inverse relationship. So as the amount of time goes down, the amount of power goes up, and they have the same distance, same mass, so B is also going to be greater than A. So good candidate for B right now to be the overall winner. If we compare B to D, D goes twice the distance. All right, so that should make that's favoring D. But compare the time, right? The time here, 25 to 8, it's 3 times the time, or more than 3 times the time actually. So even though it's twice the distance on top, it's more than 3 times on bottom. So I think B is also beating D. So right now B is we can confirm B is the first. It is the largest. So here put B first. So we don't have to worry about B anymore. Let's compare A and C. All right. A has more mass than C. C has less time, but they both are going the same distance. How do we think that's going to go? Interesting. So if you're looking at this, a 10 to 8 ratio is a 5 to 4 ratio. So their time difference from each other is a ratio of 5 to 4. But let's make sure I'm doing this right. I think this might also be a 5 to 4 ratio. Let's look here. If you divide both of those by 8, you get, 80 divided by 8 is 10. 64 divided by 8 is 8. So it's another 10 to 8 ratio of their masses, but in the reverse direction. This one has more mass, but also has more time. So the mass favors A, the time does not favor A, and they're going the same distance. But the ratios are exactly opposite, so those should be equivalent. So A and C should be equal to each other. Interesting. So now all we have to do is compare one of those with D. So I'm going to compare A to D because they have the same mass, and that should just make things easier. So D is twice as much vertical gain, which would favor the power, but A is less than half, right? So D has twice as much height, but it has 2.5 times as much time, and more time means less power. So A is actually going to have more power than D, and since A is equal to C, they both have more power than D. So B, then we have A equal to C, so A and C occupy the same spot, and then at the end, D. That's a good one. I like that, especially because you can solve it all with ratios, so you don't actually have to compute the power for anybody. All right. Hopefully this is helpful to you in solving work and power problems.